Well, hey everybody, welcome to this little video lecture on matter and energy. And I want to remind you that you matter. Unless you multiply yourself by the speed of light squared, then you energy. Ayo! Got me, legend. I know. You're welcome. It's a treat, really, for me. Okay, matter and energy. Literally, this lesson is going to let you describe the entire universe, because the entire universe is matter and energy, right? It's stuff, and then it's the things that kind of move this stuff, is kind of one way to look at it. The entire universe, right? Everything that is considered reality. Kind of trippy, right? Let's see. Okay, so first up, here is matter, right? So notice my little guy in the corner here. Let's take notes on this because this is important. Every bit of stuff, anything in the universe that's sort of stuff, is made out of matter. And matter is anything that has mass and takes up space. So sorry, that's not the right tool. Anything that has mass and takes up space, right? So even if it's really tiny, it's still taking up some space. And matter is built out of atoms. We will spend more time in this class talking about atoms and what atoms themselves are made of, but this sort of building block of matter is the atom. And over here, what you're seeing in this picture is actually an image of a hydrogen atom that scientists recently were able to capture. Doesn't look like a whole lot, but atoms are kind of weird, so I wouldn't expect a whole lot. All right, so that's matter as you might define it. And then here's something interesting. In the 1930s, there were some scientists who looked at spinning galaxies, and they said, there's something wrong here. The rate at which they're spinning could not be explained by the amount of normal matter, the amount of stuff we could see in the stars sitting out there. So they concluded that some kind of dark matter is out there, and that dark matter is thought to be much more common than normal matter. Several times more common than normal matter, but it's called dark because we can't see it or sense it in any way that we know of. And science still has no real idea what this is. Notice I'm saying don't take notes on this. You don't need to know this. This is just fascinating stuff. That we don't know what most of the universe is actually made of. We know what our matter, the stuff that we can see, is made of, but there's all this other stuff out there, and we really don't know what it's made of. Okay, how do we measure matter? We measure the amount of matter in an object using mass. And mass is something you may be familiar with because you figured out using a scale like this, right? And the metric system, so the system that you use in science and the system that most countries that aren't the United States use, we also call that system the SI system. That's its base unit, the sort of standard unit for mass is the gram, right? And you can even see in this little digital scale here, it says 0.00 little g for grams. So important to know, mass is the measure of how much matter is in an object, and that we use this unit called the gram, and sometimes we add kilo or milli or something like that to show fractions of it, but the gram is the important part here. Okay, so weight. We need to remember that weight is a different concept than mass, okay? So weight, we think of weight. In our American system, we have the pound, which is a measure of weight, and we think of weight as, I weigh this much, right? But you weigh that much because gravity is pulling on you that hard, right? It's pulling you towards the center of the earth with a certain amount of force, and that's your weight. In the metric system, the SI system, we use this base unit called the Newton, obviously named after Isaac Newton. So you would describe your weight in terms of newtons. Notice I did not say kilograms because that is again a measure of your mass. And here's a really important point I want to make sure to overemphasize. The mass of an object is always the same, right? But the weight depends on the force of gravity. So on Earth, objects always have the same weight, right? But sometimes we're not on Earth. Well, Maybe some of you are. I'm usually on Earth. But every once in a while, something else goes to another place, and its weight changes, right? So here's a good example. Let's say you have a mass of 50 kilograms. A mass of 50 kilograms. On Earth, you would have a weight of 110 pounds, which in the metric system is 490 newtons. On Mars, however, Mars is a smaller planet. Obviously, as you can see in this little cartoon, Mars is a smaller planet. It has a smaller mass and therefore less gravity. So gravity is 38% of what it is on Earth, and you would only weigh 42 pounds or 190 newtons. So you would feel like you weighed a heck of a lot less, and actually you would be able to jump a whole lot higher and walk around a whole lot easier on Mars, other than the fact that there's no air to breathe. Okay, welcome to my little demonstration on mass, and let me show you what we've got here. We've got a beaker full of water. We've got one of these. This is an Alka-Seltzer tablet. If you're not familiar with Alka-Seltzer, you drop it into some water, it fizzes like crazy, and then you drink that thing, and that makes you feel better if you have heartburn or something like that. And I've got a whiteboard over here so I can take some data, and this is a fairly accurate, fairly precise digital scale I borrowed from one of the chemistry teachers. So what we're going to do is we're going to see what happens to the mass when we put the Alka-Seltzer tablet into the water. So first let's take the mass of the things individually. I put the Alka-Seltzer tablet on the scale, and I'm getting 3.22 grams. So I'm writing that down so that we know, and then I'm going to take that off. And next, let's see, what is the mass of the beaker with water? So that's 119.42 grams. Let's add them up so that we know what the total is, and we can compare that to the total after we actually put that in there. So this is going to become 122.64 grams, right? So the mass, when we simply add them, the mass of the beaker and with the water and the Alka-Seltzer tablet come out to 122.64 grams. Let's see what happens. Are we going to get that after we drop this tablet in? Ready? Go. Okay, right around 122.64, still fizzing though. Well, it seems to be changing. Changing and changing and changing and changing and changing and changing. And it's going down, right? Not an amazing amount, but so far we've already lost 0.3 of a gram. And it's still going down as the fizzing's happening. So now it's down to, let's see if we can get it to stop moving. It's down to 122.24 grams, 122.23 grams. And if we subtract those, we'll see that what we lost was 0.41 grams. Not a massive amount, but some amount of mass did disappear. Okay, now mass is conserved. And in what I just showed you in that video was one of these illustrations that the mass has to go somewhere, right? So we had that initial mass of Alka-Seltzer, water, and beaker, and then some of it went somewhere. And the key here is that it went somewhere out into the air because I didn't close the system. In a completely closed system, the mass isn't going anywhere. So that's called the law of conservation of mass, sometimes called the law of conservation of matter, same thing. And it says that whatever goes into a chemical equation or chemical reaction and what comes out of it must always be equal. And we'll get to chemical reactions later on, but that's important. But we really just need to remember that the mass doesn't appear or disappear out of nowhere. So what must have happened in that demonstration was, after the reaction, some of the mass of the original tablet and water became gas that went out into the air. And it wasn't a large fraction of it, but it was enough that with that scale we could measure it. Okay, now continuing on our story of what is literally everything in the universe made out of, let's talk about energy. So everything that happens in the universe is because of energy, right? So the stuff is matter, and what happens is energy. And what is energy? It's actually kind of weirder than or not weirder, but it's a little harder to get your head around than you might think. Energy is the ability to do work. And work is a specific thing that we define in physics as what happens when force is used to move an object, right? Force is used to move an object, so that's work, right? It's a specific actual definition. So anytime you are sort of maybe pushing something, you are doing work, you're using energy. Also, energy is used to heat up anything that's made out of matter, right? So that's the concept of energy. And here's another, right? It's totally the same. It should look the same. Don't take notes on this. But there's also dark energy. So in the 1990s, scientists were measuring really far away items in the universe, and realized that the universe is expanding, which we figured, but the rate at which it's expanding is going up, right? We had actually thought it would be slowly contracting, but it's actually going up. And that expansion, the rate of that is accelerating. And it's going faster than the speed of light, right? Which is super weird because we think that light should be some kind of universal speed limit. But individual faraway galaxies are actually spreading apart at faster than the speed of light, and that speed is getting higher. Why? We have no idea, right? So we just say there's something called dark energy out there, and it's thought to be stretching out the universe. And we actually think, because as you'll see later, mass and energy really are two sides of the same coin, that dark energy makes up over 70% of all of the stuff that is the universe. Whoa. Okay, so energy can only be observed in how it affects matter, right? We can't see energy, we can only see what happens because of energy. And the base unit for it in the metric system, or the SI system, is the joule. Joule, joule. So that's energy. We measure it in joules. And here's two kinds of energy that we commonly will talk about: potential and kinetic, right? Potential and kinetic. And here's a good illustration. These people are standing on top of a very serious looking ski slope here. They have a lot of potential energy because they are much higher than what's down here, where they could start moving really fast. And here's some guy, I don't know who that could be, shredding the gnar, right? And as he moves, he has kinetic energy. That's the energy of movement. It also happens to be the energy of heat, because heat is actually just particles in motion, as we will talk about later. Okay, hello and welcome to my demonstration on conservation of energy. So check it out. I have a tennis ball that I have attached to the ceiling. There's a washer under there just to help the string not go through the ball. And what I'm going to do is I am going to pull it back and let it swing and see what it does. So if I stand back here and I draw the ball all the way up to my nose, after I let it go, do you think I'm going to get hit in the face? Take a moment and think about it. This is going to swing out and it's going to swing back. Is it going to hit me in the face? Let's take a look. No. Luckily, I'm safe. So the question is, why? Okay, and so what you just saw was an illustration of the law of conservation of energy. So I knew I wasn't going to be hit in the face because I know that it can't get energy out of nowhere. All I did was let it go, and it can't come back to higher than its starting point. Unless I had pushed it, which would have been an addition of energy. I didn't want to add any energy in there. I also knew it was going to lose some because there's friction between where the string is and the ceiling, and there's also air resistance as the ball moves through the air. So I knew it wasn't going to even come back to where it started. So I knew that because energy is conserved and some of it would be lost to heat in certain places, it wouldn't hit me in the face. Right? So the law of conservation of energy, just like the law of conservation of mass, tells us this stuff doesn't come from nowhere or go to nowhere. It only gets changed from one form to another. And that is a critical part of understanding how our modern world works. All right, I hope you learned something about what the entire universe is made out of, and I will see you next time.